so he came to me and told me the situation. I said, you understand that I am going to be on your case all the time, and you are going to hate me. I said, but you're going to finish. You're going to finish for that kid, child. I said, because, you know, you get a degree and you're going to be much more marketable. And so he finished over the spring.
Fine.
And I did give him a very hard time.
Yeah. Can be hard. Huh?
Hey.
Yeah, Nash.
Oh, this is recopying notes.
Oh.
It's helpful to reorganize my notes and think about the stuff that I wrote down while I was hurriedly trying to. I looked over some of my notes from, because I still have things from my undergraduate that I've kept.
Amazing, good.
And I looked over some notes from, I think it was like in a senior level E&M class. And I was looking at my notes and thinking to myself, how did I pass this class? Because we were so disorganized.
I think you're giving yourself a hard time with that. Oh, Michael. Oh, Alia, you made it. I thought you're qualified. You're qualified. I thought you said you may not come.
Yeah, I sent you email because yesterday I wasn't feel good, but now I'm good.
Okay.
But I have a qualifier at 4 o'clock.
At 12 o'clock today?
Yes.
And you're coming to a class? Okay. I guess you're good motivated students. Great.
Hi.
Hello. Hello, how are you? Alia? Rob is asking which one is at 3 o'clock.
What? Excuse me.
Which exam is? Yeah.
The exam is 4 o'clock today.
Oh, 4 o'clock. Yeah, I'm taking that one too.
Okay.
Mom, what is this thing? Mom, can you go open it?
No, Mom.
I'm gonna go see what is this. Open it.
You need to tell us your names. I think we don't know your names. At least I don't remember. Maybe you mentioned.
He asked me, what is your name? Tell him your name.
My name is Kinda.
Canada?
No, Kinda.
Kinda. Okay. Kinda, did I say that right? How do you spell it?
K-E-N-D-A.
Okay, Kinda. Okay, nice. What are you learning today?
Minus. I'm learning minus.
You're learning your miss. Is that what you said?
No, she talking about how she subtract two number 4 minus 1, 4 minus 2 like this.
Like 5 minus 5, that's 0.
Okay, 0, huh?
Mm-hmm.
You already know 0. Cool.
Okay, yeah.
I also study 0.
Class.
Yeah, lucky. You have to learn your class.
Huh?
You have to continue your video.
You gotta continue your class.
Okay, thank you.
You
Okay,
go in my class.
okay, bye. Okay,
Bye.
bye-bye.
I'm 6 years old.
Eh? I'm almost 56-year-old.
I thought you were younger than me.
I'm 49 or something.
I'm 52.
52, so yeah, I'm almost the same. At that age, I think that much round off is okay.
You're the same age as my dad. I think he's 53.
Sorry, yeah. I think 72, yes, 48.
You forget your age?
I had to subtract all the time. I assume
Oh.
I'm 50.
Jordan
All the
got a
time?
haircut.
Yeah. Usually once a year I get tired of messing with my hair.
You know, when I just looked at you the first moment, I thought he was Dave, but he's
Batista. That's a compliment. He's in pretty good shape.
Don't you think so? He's exactly like Batista.
There's some similarities facially.
I don't know what.
He's a very large man. He was a professional wrestler who got into movies and is actually impressively enough a good actor.
Yeah. Have you seen what's the movie that he's in?
Spy something? Spy Dad or something?
One with Thor and all those guys. Oh no.
Guardians of the Galaxy.
Yeah, Guardians of the Galaxy. Yeah.
No, I haven't followed those movies.
Yeah.
Marvel, yeah.
We'll have to have a physics movie night.
Isn't he the Draxler?
Yeah, he is. His relationship with Groot is really funny to me.
With who?
With Groot, that tree.
Oh, Groot, yeah.
Yeah.
I watch Bollywood movies.
Oh yeah. I actually had a Bollywood night. One of my good friends, I don't remember any of the names of the movies, but the movies were better than I thought.
And they're pretty, often it is not considered, it's, at least in academic circles, it's not very respectable to say that, oh, you watch and I enjoy them.
I mean, that's if the point of the movie is to entertain you, they definitely did that. Yeah.
I saw a scene from one, and they were talking about the physics involved because it was the guy was playing a cop, and he spins his car in a circle and he steps out of the car.
Oh,
And the car is spinning off, and then he gets pulls the gun. And
They take it to another level altogether.
You should look at like South Indian movies. They're like, a guy kills another guy with just a banana. Yeah, one complaint that I have about Bollywood movies is like most of the movies, the plot is same, like or similar.
Yeah, true. But just to give an argument against it, like there are good movies there also. Like these are extreme versions, which are really junk movies. Yeah, they're good movies too.
Oh, you got to think about our Hollywood movies too. You got
Exactly. Yeah.
Sharknado, where tornadoes pick up sharks from the ocean and then go across the United States with sharks and tornadoes. And then you got like Inception or some movie like that. They're pretty extreme.
Yeah. Inception is great. Yeah, that's one of my favorite movies. Agreed. Yeah. Okay. Anyway, let's. Oh, there's something. I get a chance to.
This is my chance to send Aaliyah all of my positive energy for her exam today, so that she does amazing.
I was late, so number 3, I just did it now.
Thank you, John.
Answer.
Sorry, too many people talking. Yeah, Avinash was talking to me. What were you saying, Jordan? I did not.
I'm just saying this is my chance to give Aaliyah all of my positive energy for her exam later. Just pushing it all towards her.
Does it happen virtually also?
It's probably better if, what if I was infected with the virus and I was trying to send those interviews and then she'd feel sick for the exam, then it would be bad. So maybe virtual is the way.
Okay, good. Yeah. And only Aliyah is taking, right? Oh, no, Rob also is taking. Yeah, two. Yeah.
Moses is not here?
Hmm?
Moses is not here.
Moses sometimes comes a few minutes late. He should be here, I think. It's typically there. So we have, which homework is this? Homework 4, homework 5?
I think it's homework 4.
Homework 4 is still going on, 21st. Come on. So this was due September 21st, and now it's due. Is it postponed? Yeah. I think it's postponed all the way to next week, but I will be posting a new homework, so it doesn't mean that the new homework will stop. Right? So that's the way we can do. Deadlines can be a little relaxed. This one, I agree, is a little confusing, so that's okay. There's a midterm 2 coming. Monday. And there is one thing I did want to mention. I did go over your exams. Exam grades are up, which also should give you a total grade also, right? Which I haven't updated yet. That's primarily because I typically give a percentage of grade return it back based on how much extra credit you've done, which I haven't worked on yet. Typically, it is, at least in this course, probably it will be 5 to 10%. So remember that total of your grade plus 100 minus total, that's your score. Right? Let's say that's your curve total, in a sense. Okay? And y is your extra credit. It has to be less than 1 or greater than 1. So convert it. So this is extra credit. And A is what I decide. So this time I plan to do it 0.10 or somewhere between 0.5 to 1%. So you should be able to calculate that on your own. But typically what I do is I calculate it and put it as a adjusted grade. So that's just for your information. Okay. So you're eager to find out what your grade is, but I'll do that one of these days. Okay, there is one error all of you guys have been doing, or I shouldn't say all of you guys, at least it seems to be very commonly being done. So, which is, for example, if you have a vector A, this is, let's say, I hat AX plus J hat AY plus K hat is Z. And if you have the gradient operator, I times d by dx plus J hat times d by dy plus K hat times d by dz, it is okay to say that del cross A is equal to, usually you write the determinant, right? So this is d by dx, dy, d by dz, and then this is A of x, y, A of z. That's the determinant of that, and then you make sure that you operate d by dx on A of x. This could be function, right? So this could be a function of x, y, z. So that's how you operate. But if you are in, let's say, cylindrical coordinates or spherical coordinates, either way. So let's say spherical coordinates are hat A of r plus theta hat A of theta plus phi of hat A of phi. Right? Again, these are functions of r theta and phi. Now, gradient operator also has a structure. So it's d by dr plus theta hat 1 over d by z d theta plus phi hat phi hat 1 over r sine theta d by d phi, right? And this is not equal to, this is not equal to something. Right? That's wrong if I write this as r theta phi hat d by dr d by 1 over r d by d theta 1 over r sine theta d by d phi and a of r, a of theta, a of phi. That's wrong. Okay, so this seems to be a common thing some of you guys have been doing. So what is the generalized version of this? So what is the correct version of, if you want to use it in this form, which I'm not a big fan of it because it's a very specialized curl. So curl is a certain way of doing it is okay, but it's not a very generic quantity. So what do you do? I don't even remember.
1 over H1, H2, H3.
1 over H r, let's say, H theta, H phi, yeah? Or H1 is to H3 is better. Let's write it as general, yeah. Okay, yeah, if you remember, yeah.
And determinant H1 E1 hat, H2 E2 hat. D E1, D E2.
E by E1.
Oh, you're doing the scale factor method.
Yeah, I'll tell you that in a minute.
H1 component E1.
Where H1, H2, H3, as one of you guys said, is the scale factor. And H1 in our case is 1. H2 is R. And H3 is R sine theta. Right?
Where the scale factors are just the magnitudes, right, of the, is that right?
Tell it again.
No, where you get the scale factors by taking the magnitude of the,
Of E1, but this is E1 hat, notice. Yeah, by taking the magnitude of the covariant basis vector, correct? Exactly. Yeah, exactly. So this, if you want to use this, this is what you want to use. This is not okay. And I should have emphasized, I agree. Yeah, but I. Yeah. But if there's any confusion, it appears in the resource material that I posted. I think after homework 2 somewhere. So this appears in there. So yeah, so that I wanted to point out. But once you realize this, then it's good enough. Any questions? Comments, John? Oh, Moses is still. What's wrong? Okay, so we did at least 2 conservation of conservation statements, or 3, right? Charge conservation, energy conservation, and linear momentum conservation and electromagnetism. One nice thing to do this is what happens when there is an electromagnetic wave going through, then we can associate an energy. Yes, please.
So you mentioned like linear momentum in electromagnetism. Is there like an angular momentum?
Yes, there is. So there you go. Since you asked, extra credit.
I think it's actually in the book.
Exactly. Yeah, it's right. It's all.
Which
It comes
book is
right
it?
after the linear section, I'm pretty sure.
That's correct. Yeah. In fact, you can do various other things with this quantity, but derivation is pretty much simple. You just start with like what we have is dg by dt plus a partial derivative of the linear momentum density plus the divergence of the stress tensor plus the force density is equal to 0. If you want to do angular momentum, you do cross, right? Moment of a force. So you take the cross of this quantity, cross, R goes through D, so we don't have to worry about that. So this is immediately angular momentum density plus there is R cross. Notice what is it crossing it with? This is the free vector. I've already used up one of the vector, one vector remaining. So this is del cross of T. Del dot, right? So this is the second vector that it is going through, not the first component, first index, the second index, plus R cross F, which is the torque. But you have to massage this a little bit. You have to make it go through, right? Or you have to write this in the form of a divergence.
So does that mean you take divergence of that tensor and then take a curl with R?
That's what, as of now, it says. But it's not a conservation statement unless I can write a divergence of something. So that's your extra credit exercise. Write this as a divergence of some quantity. Right? You don't have to derive this since it's an extra credit. Since you asked, you should be familiar. So at least write down the expression. Right? It's only 2 steps to look into the textbook, but just the expression is good enough so that you're familiar that yeah, it is available. So typically, sometimes when I go fast on this, when I'm able to go fast, then I give a problem on angular momentum conservation also. So you can have a spherical charge which is rotating and its whole field is rotating. So it's not the easiest problem, but still one can work on. But now let's do one more example in this context, and that is a monochromatic wave coming in. It's kind of a nice simple exercise. One should know because it's a very good solution to Maxwell's equation. So let's write down Maxwell's equation. Yeah, let's write down the Maxwell's equations are so dotted with. Let me write it as D. This row. Hopefully it's clear. Dotted with B is equal to 0. Del cross E is equal to minus dB by dt, and del crossed H is equal to right, that's a true. That's a Maxwell's equations if you want. We can do a small trick here and get, or let me just derive that and then we will, I'll ask you guys what that it means. Let me take the curl of the third equation. So I have curl of third equation, which is minus d by dt of curl of B, which is mu naught times curl of H. But curl of H is the fourth Maxwell's equation. So that's the same as, and by the way, here I'm not having matter anywhere. So this is mu naught times E, and B is equal to mu naught times H. Very soon we will start talking about matter, then we have to change that vacuum properties to material properties. So this is the same as mu naught epsilon naught, second derivative of t squared times E. And when I substitute this in here, the minus, right? So it is minus mu naught d by dt of J. On the left hand side, I have del of divergence of the electric field minus of the Laplacian of the electric field. Correct? Is that? So we have been using these identities sufficiently. And let me write this in the form.
So this is how you get the wave equations?
Yes, so I was going to ask, that was my next question as to what is this equation, but that is something extra, right? So del dot E has a rho over epsilon, so it is so it is plus, so this becomes minus, that becomes plus, so it's plus del of rho over epsilon naught and minus of okay. Now let me consider the scenario at a point R where so at a point R where rho is equal to 0 and J is equal to 0. That means to say anywhere outside the charge. Right? If rho is equal to 0 and J is equal to 0, the left hand side goes away, and then I get the wave equation.
So when there's no current density, and basically saying that
That's a
there's
stronger statement than where I'm saying that there could be a source current and a source. It's just that I'm evaluating the point outside that. So if you say that there is no charge and there is no current, that's a stronger statement. I'm saying they exist, but I'm saying that at points outside that. There could be sources, they act like sources, but the fields outside that have satisfied this. And now that since you guys identified this to be a wave equation, so this is this.
Should that last term on the equation above be a plus?
Oh, this should be, I thought I moved this, so this was a minus, right? So this was minus, so I made this a minus, right? When I change the sign, bring it back here, it's a plus. Oh, this is what you mean, right? Oh, so this one is minus, so this is plus. Thank you. Is that?
That was it.
Thank you, thank you, thank you. And I should, yeah.
so partial by partial, since you can move the gradient operator and then move in. Is that basically what you did? Like
Which this step?
since the curl of the magnetic field is equal to mu naught J plus mu naught epsilon naught, is that what you're saying? Okay, never mind. I got it. I figured it out. I just talking myself through it.
Okay. If you have an equation like this, I think we mentioned did I mention it in this class or somewhere else? What are the solutions possible for this? So maybe we should point out. So if you ever have an equation like this, let's talk about one dimension first. F is equal to 1 over velocity square d square by dt square times f, right? What are the solutions possible for this? F is equal to no?
Can you actually raise the camera just a little bit? It's
Oh,
off the board slightly for me.
better, right?
Yeah, that's a lot better.
Okay. Is this readable? Should I zoom it in?
I think it's readable. It's, yeah, just write it down real quick.
That's the wave equation. What are the solutions for this?
It'd be something like a sine of kx minus omega t.
That's correct. That's surely a solution. Sine of kx, where you mean k where lambda, right? So kx minus omega t. That's correct. Where k is since we have velocity, k times omega, right? K times omega, I think is 1 over v, I guess. Am I right? 1 over 10 of v, right? V. Is that correct? C actually in this case. That's correct, very correct. But in a more generic form, that's surely one solution. Slightly more general.
You want like the E stuff, like
E stuff.
E plus or minus I omega
That's
t.
surely, that's again sine, right? That's pretty much sine itself. But notice that any function of this kind, any function you can imagine of this form, you take the x here and vt here. Probably that's what you meant.
Okay.
So any function of this kind will work. In fact, you can put a x minus vt also. Right?
I have one question.
Yes.
So is k omega is equal to c?
Did I say this
K
correctly?
is 2 pi over lambda and omega is 2 pi over t. So it should be 4 pi squared in the numerator.
Okay, what is k over omega? How is that?
And that would be 1 over velocity.
Much better. No one stopped me. Sorry. First of all, I shouldn't write that. I guess you are very tolerant of my mistakes. Okay, thank you. Thank you. Avinash? Yeah. Okay. So, notice that in general, whenever I think I remember mentioning this somewhere, d by dx square plus d by dy square plus d by dz square. So this is not even a wave equation, all right? I'll write this as a wave equation very soon. So let me write this, give it some room. Times f is equal to 0. What are the solutions for this? Right. In this case, the solution would be f is equal to ax plus by plus cz as far as a square plus b square plus c square is equal to 0. Like whenever, so you can verify this. If I do the derivative with this, I'll get an a. Take a second derivative, I'll get an a square. And derivative of f, but that will be common for all. A square plus b square plus z square. If this is 0, that's always going to be 0. Is that clear? So for example, d by dx of f is equal to a times f prime, where f prime means that it's the first derivative with the argument. Correct? So, and second derivative of f with respect to x is equal to a square times f double prime. So overall, you will get a square plus b square plus c square times the second derivative with the argument that has to go to 0. So there are two possibilities, either this is 0 or this needs to be 0. So that's a very generic way of getting this to be 0. Question?
So, so when we write df over dx is af prime, so that prime depends on x, right?
Yes, so maybe I should clarify that what I mean there. What I meant is that derivative of ax plus by plus cz of d of x times derivative of ax plus by plus cz of f. Right? This is an argument, right? So this gives me an a, and whatever this is, I keep it. Like by this, I mean the derivative with the argument. And second derivative will again give me that. Okay. And if I have, so if I have minus 1 over v square d by dt square, right? Then this is the same as I guess minus d square over v square, I suppose, has to be equal to 0. So in general, that's the solution. Right? All right. Thanks. Hopefully. Yeah. But that's correct. This is called. I think. Yeah. It was this spherical hub. Yeah. Analytic function we mentioned.
So when we so the solution, does it not depend on time?
It does depend on the time, right? Ax plus by plus cz minus vt, right? Or plus vt is also okay, it goes in the opposite direction, right? So these are the two solutions, correct? So let me write the general one. So we are doing, so in general, what is our case? I was interested in this, correct? So I would say this has a solution whenever the f is equal to f of k, like instead of ABC, I want to write k1 times x plus k2 times y plus k3 times z, and the fourth component, I say, is plus omega times t. And this is a solution as far as k1 squared plus k2 squared plus k3 squared plus omega squared, and I don't like that, so I put an I there. Do I want to put an I? No, I don't want to put an I there. How do I get this? But it can be plus or minus, right? Plus omega squared is equal to 0, right? But we want to so this is a statement going beyond this plus. So this is I. This is I plus I. And this is minus. And why is that I there? Okay. Any comments on that? Why should there be an I there?
Well, it makes the,
Actually, it's plus. Actually, minus. Yeah. That's it. Yeah. Go ahead. I mean, this should be minus. Yeah. Go ahead.
I'm gonna say that the I there would make that minus as well, wouldn't it?
Notice this is a minus sign, right? Unlike earlier, this is a minus sign, correct? And so what I'll do is that this -1, I'll replace it as I square. So that becomes an I there. And that's what I interpret in here as minus omega square. So this can be plus or minus, however I want it to be. But this quantity is minus square. Why is there a minus square? Because this is a minus sign. Right? So if you want to use the earlier statement, then you want to replace the -1 with I square. So some features in there, yeah, some. In general, these are called harmonic solutions to the Laplacian, right? So okay, so if you accept that much, so my electric field solutions, all this part of my electric field went into a tangent. So the solutions for this are whenever k1x, k2y, this is nothing but k dotted with x. So this is a solution whenever I have a function k dotted with x minus of omega t, or I could have other way, right? So plus another solution. Yeah, let me just write. There are many possibilities there actually. So let me just say that that's a possibility. But then any function, for that matter, even here, can be Fourier transformed. So that was what I think some of you guys were thinking in terms of sine and cosine. You can write it, of course, and a particular solution of this. So a monochromatic wave, let's say. Monochromatic wave. Actually, no, I have to define Fourier transform for you guys, right? Because in this course, I started that. So once, let me do that. So that's your wave solution. But let me take a small deviation, which well, must be familiar, but at least I have to state this. So this is a small Fourier transformation, which basically means that I can expand any function in terms of some components. Best example is think of a function of time. Like if I have a function of time, I would like to write it in terms of sine and cosines. So I would say A0 plus A1 sine of omega t plus A2 sine of 2 omega t plus the 1 And I can also do
Sorry.
didn't like my voice. Fourier transform, it doesn't like, huh? P2 cosine of 2 omega t plus so on. Right? Notice this is pretty much the way to interpret this is that think of music. This is any function of time. That's music basically. Some function as time goes, you have a amplitude, and it can be written in terms of modes, right? 1 mode, 2 mode, 3 mode, and so on. Replace the sine with cosines. This is nothing but exponential of m going from minus infinity to plus infinity, and I can recollect all this. Let's call it. Let me call them Cm times e raised to I m omega t. So that m goes from minus infinity to plus infinity, and these are the coefficients. So one should imagine this or interpret this as these are unit vectors. If you want to think of it as whatever we did earlier, these are basis vectors. In this context, they are called eigenvectors. If you are doing a vector space, finite vector space, you call them basis vectors. Here they are called eigenvectors. In fact, this is a Fourier expansion, so you call it Fourier eigenvectors. Or eigenvectors or eigenfunctions. Eigenfunctions or better. And these are the components. Like when I write a vector, I ask what's the component in the x direction, what is the component in the y direction, what is the component in the z direction, and these are the components in these along these eigen functions. This is all good when this is a finite domain. When time is having a finite domain, then this is good. In general, you want to make this a continuous variable. So if t was going all the way to infinity and going all the way to minus infinity, then you want to extend this to f of t is equal to, instead of a sum, this now gets upgraded to an integral. And I can put the 2 pi there also. I can absorb that into the Cm. It doesn't matter, but since we will be using this continuous Fourier transform, and I want to fix the notation that we will be using, that's minus infinity to plus infinity, e raised to minus I omega t, and this will be f of omega. Now this should be f tilde of omega. That's an entirely different function. This is the coefficient of this. So these are the Fourier eigenfunctions. Same idea, and often I will even drop this tilde on top of this, and it will be understood that if it's a function of omega here, a function of t here, but they're in different functions. So that's just for convenience, I will drop that. Okay. I should be able to invert it. For example, you can ask, okay, given a function, what are its components? So how do you find those components? You can invert this. So this is the inverse Fourier transform. So this is minus infinity to plus infinity dt e raised to plus I omega t this time, and f of t. Notice where the 2 pi sets are almost different. People have different ways of doing it. Sometimes you equally distribute the 2 pi. Sometimes you put the 2 pi on the t and so on. So notice the difference. But there is one thing that I've noticed is very common, is that whenever you're doing quantum mechanics for for a particular reason, you distribute this actually equally and say this is square root of 2 pi dash square root of 2 pi dash. And even when I am doing a particular system in quantum mechanics, I usually switch over to that. But in this whole course, we will use Fourier transformation in this one. This is the Fourier transformation in time. I can do this in position also. In fact, there are 3 spatial positions. So electric field well, when I Fourier transform this, I can Fourier transform into all of the space components, all of the times components, and do the same idea. And this will be d cube k now. The Fourier transform of R is k, so this is like momentum if you want. That's 2 pi cube. That is at time. This is dt. Sorry, frequency. Add on frequency. That's 2 pi. And I don't say this here. This is all. So this is 3 integrals in here. So they are all from minus infinity to plus infinity. Right, so there are 4 integrals in there. They all combine together to have I k dotted with R minus I omega t. And the Fourier transform will be called E. Now notice this is where the flutter comes in. I should principle say this is tilde, right? That's a new function. But it will be clear if I always make sure that I write the dependence in there. Whenever it's a frequency dependence, I would say that that's a different function. Yes. Understand that these 2 are not the very same functions. It should be tilde, but I just, to avoid clutter, I just remove them. Okay. That leads to the question which is generally I ask is why is there a minus sign there? Why did I choose, so this was my notation for time, but then when I did it for position, it seems like I chose a plus sign. Why is there a minus sign there? Any guesses? It's not obvious at this point. It's slightly more than a notation, but even if I write plus, it is perfectly fine. Because if I do the integral, who cares whether I go from minus infinity to plus infinity or plus infinity to minus infinity? I'm actually summing up, so that should be perfectly fine if I take care of the signs correctly. But it is preferred to write it in this manner. Any thoughts on that? Why do you write k dotted with R minus omega t? I might have mentioned this in another context before.
It has something to do with direction, right?
No, I think you're thinking of f of x minus vt, right? And f of x plus vt. In this case, yes, the interpretation is that this is interpreted as a wave going to the right. This is interpreted as a wave going to the left. But this is slightly, pretty much the same reasoning, but why would I prefer to write it as minus? That was my question.
Does it have to do anything with plane wave?
Plane wave, no, it has to do with relativity. Like that's an invariant quantity. So notice that when you go to relativity, instead of k dotted with r, there is a time also, right? You extend your space. So this is like a dot product. And now there is a 4th component, there is a time, and there is an omega. That's what the frequency, and these are the 4th dot product, but that comes with a negative sign. Like if you have seen any sort of Lorentz transformation, there is a negative sign there. So this guarantees that this is a Lorentz invariant. Okay. So, but again, as you guys said, this is not strict. If I write plus I omega, there's absolutely nothing wrong. It doesn't make it forget the Lorentz invariants at all. But this brings out the Lorentz invariants, right? But we want worry too much about that. So that's your Fourier transform, and then if I were to invert this, I have k omega is equal to d cube r dt, all going from minus infinity to plus infinity. This is all space, right? Going from minus infinity to plus infinity, and just change the signs and you're good. Okay. So it's good to clarify at this point, what do I mean by monochromatic wave? Monochromatic wave is neither of this. It's not this, and it's not this either.
Like a laser, right?
Tell that again?
It's like a laser, right?
Yeah, it is like a laser, exactly. It's like a laser. It keeps running, right? It's like a laser, but it's neither one of this. So what do I mean by that? So what I do is I only partially Fourier transform. Who says that I should do all four at the same time? I will Fourier transform in time, but not Fourier transform in position. So this is always a possibility. So I say E of RT or R of omega now. First let me E of RT, yeah, just so Fourier transform only in time, and that gives me d omega by 2 pi e raised to minus I omega t and e of r omega. See, I'm using the same function for all. It's understood that every time I Fourier transform, it's a different function. Right? The components need not be the same. And e of r omega will be dt e raised to I omega t e of rt. Okay, so now let's say let E of RT be equal to E naught and exponential of I k dotted with r minus I omega t. Right? What is that? That seems like a sine and a cosine, correct? But I say that some rough. If I say that this is the electric field, that is probably an issue there. What could be the issue?
Ask that question one more time.
First I state that electric field is this, and then I myself say that, oh, that might not be okay. Is that okay? Like that, and what I have in mind is that electric field is measured in a lab. It should have real quantity, right? It should be real. Right? Electric field is supposed to be a real quantity, but this is imaginary, right? So it's probably not okay to say exponential. So let me say cosine. Okay.
But what if you just kept the real part?
That's good enough. That's the same thing. Yes, that's good enough. So another way of writing this is E naught, a real part of exponential of I k dotted with r minus I omega t. Yeah, good enough.
And that cannot also be imaginary?
In this case, no. So if you really, so E is real. Here E is real, the way I have constructed it, because electric field has to be real. This has to be real, that has to be real. Okay. So that's a condition we will impose. But, and this is nothing but, let me explicitly write this, E naught 1 over 2. Cosine is nothing but 2 exponentials, right? I k dotted with r minus I omega t plus e raised to minus I k dotted with r plus I omega. Right? We understand that expansion. So that's E of RT, but I'm interested in this quantity here. What is the Fourier transform in time? Okay. And so I put it in there, right? I substitute this in there. So minus infinity to plus infinity dt e raised to I omega t. Maybe let me, oh, you're wrong. Let me introduce one point here that let me not put a zeros here everywhere. It means that that's the characteristic of the wave, right? So this is not, because there are k and omegas in the integral also. These are all properties of this particular configuration we are having. So then I don't have to worry about this omega, but it will come out to be related. So that's E of RT. I will just substitute that in there, right? So that's E naught 1 over 2 and e raised to I k naught dotted with r minus I omega t plus k now does not depend on time, they can come out. So this is E naught can come out. Right, so 1 by 2 e raised to I k naught dotted with r. And that is an integral now. Minus infinity to plus infinity dt e raised to I omega minus omega naught t. And the second one is minus I k naught r integral dt e raised to I omega plus omega naught t. You get what is that integral equal to? What is this integral equal to? This one? The standard integral?
Just e to the I omega minus omega times t.
Yeah, but. If t was equal to 0, what is it?
1.
No. So suppose
That's the integral, oh, just t?
t, but then you have to put the limits.
So negative infinity to infinity?
Yes, so which is pretty big number probably, right? It's the length of the whole time. Correct?
Yeah.
Which is infinity. Agreed?
Mm-hmm.
But that is only when t is equal to 0. What is it when t is not equal to 0?
I have one question. So when we say time goes from negative infinity to positive infinity, do we mean negative infinity is all the way in the past and positive infinity is in the future with
That's-
0 being the present?
That's right. Yeah, 0 could be the percent. Yes. We are somewhere inside that minus infinity to plus infinity. So I was saying that this, so let's look at this integral. Dt e raised to I omega t. Right? When t is equal to 0, this seems to be infinity. But if t is not equal to 0, this is a cosine and a sine function. There's a cosine function and a time function. What is integral of cosine from, let's say, from finite region to a positive, or let's say in a definite cycle?
Could be any function, right?
It could be anything, but if I always go in multiples of this period, right, that is always 0. Right? So you can formalize this and say that this is always 0. Again, you have to say that this is in multiples of, so you have to say minus n times the wavelength lambda, and you have to say it is plus n times the wavelength of lambda, and then take the limit n tends to infinity. Then this is basically a delta function in frequency. Okay? And that's a standard identity that this is actually a delta function. So what I've invoked is, I've told you that this is minus infinity to plus infinity dt e raised to I omega t is 2 pi times a delta function. That 2 pi, I did not motivate much, but that's primarily coming from that wavelength that I talked about. Okay. If that is the case, then you get here E naught, and this should make a little more physical sense. This is e raised to I k naught dotted with r, omega minus omega naught. Right? What does that mean? The frequency has to be omega naught. That's what it means to say monochromatic wave, right? Frequency is a fixed one, plus e raised to minus I k naught r dotted with r, delta of omega plus omega naught. Now notice, is this a real quantity or an imaginary quantity? This electric field here. I earlier said that R and T is real. Electric field in position and time is real. But this is not real. It doesn't have to be real. In fact, in general, it's not real. Okay, so because you went into the Fourier space, it is typically not real. Right? Electric field is not real. We will often drop this omega delta function of omega times omega naught, and we'll drop this also and talk about one frequency component, which is one of the omega naught component, and we will talk about, so for our purposes, so a monochromatic wave in the position space, this is equal to E naught times cosine of k dotted with r minus omega t. If you want to write as exponential, that's perfectly fine. In the partial Fourier transform space, that means to say time in the frequency space, let us say, this is equal to E naught 2 pi over 2, and we have e raised to I k dotted with r and delta function of omega minus omega naught plus this is a good thing to notice that in one space there is no, like if I were to ask what is the position of this wave, like the monochromatic wave, what is the position of that quantity? it is spread out, right? It goes from all the way from minus infinity to plus infinity. So that is no meaning to say what is the position in this place. In here, we are talking about time, right? But it has a very unique frequency. Right? So the moment you take away the information about time, the frequency becomes fixed. And if you were to remove the specify the information of time too precisely, the frequency gets spread out. So that's a very standard thing that comes in a Fourier transform function, like spread in frequency and spread in position and spread in wavelength is inversely related to each other. For our component, for us component, Fourier component, Fourier component of electric field will be, we will often take only one piece out of this. We'll even absorb this into that. So, or imagine that this also is absorbed into that. That's a better way of saying it. And we will often like to say the Fourier component of an electric field is just this, with the imagination that E naught absorbs everything to one component. And we would like to ask, how does the Maxwell's equations work with this information, and how does your energy density go, how does the momentum go, and so on. That's what we want. I was hoping to do all this quickly, but I think I'll continue this. I think one thing I can do is, there is one nice feature about Fourier space, right, or Fourier components. It's the following. This is a trick, right? Right. It's a trick. Often you have derivatives showing up. So think of time derivative of electric field as a function of time. You immediately want to go into the Fourier space. So this would be time derivative of the omega over 2 pi, and this is exponential minus I omega t times e of r omega. This time derivative only hits the eigenfunction and not on the component. It hits only on the eigenfunction, but then it has to be inside the integral because it brings down an omega. So that's minus I omega times e of r omega. That means to say that whatever the time derivative of the electric field in position space is equivalent. If you want to look into the Fourier space and investigate how is the time derivative working, it is the same as an algebraic quantity E. So this is R of t, notice, maybe I should clarify, this is R of t and this is R of omega. So this is how time derivative works in the Fourier space. And this will be a continuous phenomena that we will see. If something is happening in real space, we want to investigate or we want to have an insight of how things are happening in the Fourier space. So this is just algebraic. Time derivative becomes simply a quantity multiplication quantity in there. So extra credit, let's say, this probably might be difficult. This is what we are going to do next in the next class. Rewrite the Maxwell's equation in terms of E of RT, E of R omega, and D of R omega. So that means to say Maxwell's equations are written in position and time. You can ask, what are the Maxwell's equations in position and frequency? Okay, so, and again, don't worry too much about it, just make an attempt on it. We'll do this in the next class. And I'll stop here. Thank you.
I have a quick question for you. When you do Fourier transforms and stuff, when you look at like a wave, you know, like when you see the representation of like from point A to point B, and at point A and at point B, the transform doesn't give you like a smooth line. Like, you know, when you have the oscillation at the endpoints, they're like peaks, and then it goes into the smooth.
I think I don't get it. Can you repeat it?
You have to formulate the question or like send you a drawing or something, because I don't know, I'm not sure I know how to like explain it mathematically. I'm just asking. Whenever you,
I heard that you have something like this. Is that what
yes, but you know, and you can make that center area closer and closer to a line.
Yeah.
But there's always, at the edges, there's always like that.
This leads to issues related to, it's called Gibbs phenomenon. I think it's good to read this. It is a common caveat you encounter when you're doing Fourier transformation, but most probably we won't encounter that. Okay? We will stay away from that.
Okay.
So it's a good thing to point out, and I would encourage others to look into it. It's a caveat that comes in, but it can be avoided. The nice neat, or you call it neat, but the issues that comes up, for example, if you're adding some numbers, you can get the wrong results because of this. I typically give this in math. Yeah, if we are doing math methods, when we do Fourier transform, I usually give an example where you get the wrong result, and you have to capture the correct result if you're very careful. Yeah, so probably we'll see this in the math methods. So good point. Yeah, that's good to see that. Yeah. Okay, thank you. And
Thank you.
Thank you.
best wishes, Alia, for your qualifier, and Rob left. Yeah. Okay. Okay. Enjoy, guys.
Bye-bye.
See you guys.
Yeah. Bye bye.
And do you make qualifiers?
No, I don't.